Okay, we're going to do a quick review of simplifying radicals because we're going to use this when we talk about the Pythagorean theorem and the distance formula. So it says when simplifying radicals, we sometimes use a factor tree. So if you remember a factor tree, so if I talk about 72 and I break it into its factor tree, I first think about factors that multiply to be 72, so like 8 and 9. And then I say, okay, well 8 breaks into 4 and 2, 9 breaks into 3 and 3, 4 breaks into 2 and 2, and we continue to carry those numbers down. Okay. So it says when we're trying to figure out the square root of 72, what we're doing is we're looking for numbers that are written twice. So notice how I have two 2's. Well, 2 times 2 is 4, and we know that the square root of 4 is just plain 2. So when we take the square root of 4, we're left with a 2 on the outside. And when we take the square root of 3 times 3, which was 9, we're left with a 3. And those are no longer under square roots because I took the square root of them, and the square root of 9 was just 3. Okay, so if you notice there's one lonely number, it doesn't have a pair. And so if there's any numbers that were not circled, we write those inside the square root still. So it's going to be square root of 2 still, because it didn't have a pair. If it had 2 times 2, that would be the square root of 4, which is then 2. And so our final solution is 6 square root of 2. So we take these two numbers and we multiply them together to give that 6. Okay, so that's how we would do the square root of 72. So on the next one, square root of 64, I think we all know that that's going to be 8. But we can kind of look at the process and we can say, okay, 8 and 8, 4 and 2, 4 and 2. So it breaks down to 3 2's there, another 3 2's here. And as we look for pairs of numbers, we have a pair of 2's, so we're left with a 2. Because that was just the square root of 4, which is 2. We have another 2 times 2, so square root of 4 again is another 2, and square root of 4 is again another 2. And then this time we don't have anything inside that square root. There's nothing there. So it's just 2 times 2 times 2, which is the answer 8. So that's why that works. So the same thing with square root of 144. I think you probably know that that's 12, so we'll just leave it as 12. But things like square root of 32, I know you can put that into your calculator. You can get a decimal number. So like the square root of 32, let's see, what would it be between? Well, it's not quite the square root of 36, right, which would be 6. And it's a little bit more than the square root of 25. So it's something between 5 and 6. But I want the exact answer. And an exact answer would involve a square root. So we don't like to round things if we don't have to. And we'll talk about that a lot throughout geometry. A lot of times I'm not going to allow you to round your answers. I want them as exact as possible. All right, so square root of 32. 32 breaks into 8 and 4. 8, we've just learned, breaks into 3 2's, 2 times 2 times 2. And 4 breaks into 2 more 2's. So we have 5 2's. So as I look for my pairs, I have 2 and another 2. And then inside the square root, I'm left with the 2 that was there. So I have a 2 on the inside. So my answer is 4 root 2. And that's the exact answer. So same idea for 124. So, I always tutor people and they're like, oh, I know 2 goes into it. So it's 2 and 62. And then they just keep putting 2 into it. But this one's only a couple. So it's 2 times 2 times 31. And 31 ends up being a prime number. So we have 2 times 2, which gives us a 2 when I take the square root, and then I have square root of 31. Okay, the next one. Again, like I was saying, most people don't know at first. They're like, oh, I know at least 2 goes into it. So I get 512, 2 and 256, 2 and 128, and it just keeps going and going and going. So it's kind of a lopsided tree here. So then at least we get to 64, and we're like, okay, that's going to be 8 and 8. So then we have 2 times 2 times 2, 2 times 2 times 2. We had a 2 from that one, a 2 from this one, a 2 from there, and a 2 from there. That's a lot of 2's. It's 10 2's if you count them. So that means that I would have 5 pairs of 2, so I'm going to have 2 times 2 times 2 times 2 times 2. And if you multiply that out, 2 times 2 is 4, times another one is 8, times another one is 16, times another one is 32. So the answer is 32. So you can see that sometimes the factor tree method can be kind of annoying, right? We don't like to list out all of the factors, especially on something like the square root of 1024, because it goes on for a very long time. Okay, so when we look at something like the square root of 500, it's convenient to think about what we call perfect squares. So perfect squares are the numbers like 1, 4, 9, 16, 25. Do you guys all know these numbers? So we're saying 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared would be 64. So these are what we call perfect squares. So if we can think about a large perfect square that goes into 500 that we're able to take the square root of, it saves us a lot of work. So this is the goal. Eventually, when you guys get past geometry and you're in pre-calc, this is going to be like second nature to you. You're going to know how to do the square root of 500 right away. So we want to think about a number that I can take the square root of evenly that goes into 500. Well, what about 100? Isn't that a perfect square? The square root of 100 is 10, right? And we're left with 5. So I have the square root of 100, and I have 5. And then I just go ahead and I take the square root of 100. So it's basically like I'm doing a big factor tree, and I'm saying I have 100 and I have 5. And then I'm like, oh, 100 is 10 times 10. And then I'm just stopping there. I'm not breaking it down into its prime factorization. I'm just saying, oh, 10 times 10. The square root of 10 times 10 is just 10. And then I'm left with the square root of 5. So the answer is 10 square root of 5. Okay, so do you guys see how that works? So we're going to do a couple like that, where we're going to try to skip the factor tree method because we understand why that works now. And we're just going to do a little shortcut here. Okay, so the next one is the square root of 20 times the square root of 5. Well, you can actually multiply those together and say it's the square root of 100. And the square root of 100 we know is 10. Okay, so same thing here. This is the square root of 36 divided by 3. Well, the square root of 36 we know is 6 divided by 3, so our answer then is 2. And then we have things like 4 divided by the square root of 2. Okay, and there's kind of a long story on why we do this. I'm going to try to simplify it for you. So we do not like to have 4 divided by square root of 2. And this takes us way back in the math history when we were trying to do, like square root of 2 is 1.414. Can you imagine doing long division with 4 divided by 1.414? You'd have to add the 3 zeros. You'd say, oh, it goes in this many times. I don't even know how many times, twice. 3 times I think would be too big. And then you'd be like, okay, well, that's 2.828. You'd subtract it out, and you'd continue doing that long division. That is very messy. So before the days of calculators, this was a hard number to approximate. 4 divided by square root of 2, we didn't like finding that. So we started using our smarts. We started thinking, well, I know that if I multiply by like 5 over 5, let's say, that's like multiplying by 1, right? So multiplying by 1 doesn't change the number. So 20 divided by 5 root 2 is actually the same number. You can check on your calculator. It's the same, but that doesn't help us much. So what we do is we multiply by the square root of 2 over square root of 2. And the reason that's nice for us is because the bottom becomes the square root of 4. And the square root of 4, well, 4 is a perfect square, so we can take the square root of it. So that's what we're going to do. We're going to multiply by the square root of 2 over the square root of 2. And on the top, we have 4 divided by this, or 4 times the square root of 2. And on the bottom, we have the square root of 4, which is just 2. Now it's kind of like 4x over 2. And 4x divided by 2 in algebra, you know, ends up being 2x. So we're kind of ignoring this part. We're treating it like an x. So this becomes 2 square root of 2 in the end. So let's think back. This, super hard to do. Can you guys all do 2 times 1.414 in your head? Right, 2 times the square root of 2. Is it easy to find a decimal approximation? Can you double 1.414 in your head? Try it. 1.414 plus another 1.414 is 2.828. We can all do that in our head. And so that's why we started rationalizing the denominator. That's what we call it, rationalizing the denominator. So we have weird rules in math, and one of our weird rules is when we have a square root on the bottom, we can't leave the square root in the bottom. We have to simplify it. And we care about that through, you know, geometry, algebra 2, we kind of care about it. And then once you get to pre-calc and AP calc, we stop caring and we let you leave it as 4 over square root of 2. So I'm sorry, I'm going to put you through the pain in geometry of rationalizing the denominator. So this next one, I have the square root of 3 on the bottom. Well, what do I need in order to make that something I can take the square root of? If I multiply by another square root of 3, then I get a 3 on the bottom because it becomes square root of 9, right? And then on the top, I have 15 root 3. So if I had 15x divided by 3, that would work out to be 5x. So this is going to be 5 square root of 3 in the end. Okay, so try the next one. We multiply by the square root of 5 over square root of 5. On the bottom, we get just plain 5 because it was the square root of 25. On the top, we get negative 25 root 5. So we get negative 5 root 5 in the end. But don't always do this method, because on this next one, I could multiply by the square root of 6 over square root of 6. But there's an easier way on this one. So I'm going to show you a trick. So just like we did up in number 7, where we combined, we were like, oh, if I have a square root times a square root, it's just going to be the square root of that number multiplied. Like 20 times 5 was 100. Let's do that here. So let's see if 162, if I can divide by 6. So you can divide by 2 and then divide by 3. Do one thing at a time, or you can do it all together. So it goes in 2 times. I'm left with 42. So 6 times 7 is what makes 42. So this ends up being negative square root of 27 because we just brought that 162 over 6 and we simplified that. Okay, so we have the square root of 27. Well, can that reduce down? So think to our factor tree. So if I have 27, well, that's 9 and 3, 3, 3, and a 3. So I have a pair of 3's. So when I have that pair of 3's, I have the square root of 9, which is just plain 3 on the outside, and then I'm left with the square root of 3. So that's how we simplify that. Okay, so sometimes we don't need, I don't know if I have examples of any more of these, but sometimes we don't need to multiply by what that denominator is. So on number 12, you just saw that we didn't need to multiply by the square root of 6 over square root of 6. You could, it just takes a little bit longer. But the same kind of thing happens on something like, let me give you an example, like 4 divided by the square root of 8. Right, I don't need to multiply by the square root of 8. I could. Really all I need, though, to make the bottom into a perfect square is I just need the square root of 2. Because then the bottom becomes the square root of 16. And we know the square root of 16 is 4. So we have 4 root 2 on top divided by 4, so it ends up just being root 2. So that's the easiest way to do those types of problems. So never go too big. Think about the easiest way to simplify our square roots. All right, hopefully that makes sense. If you guys are having trouble, remember you can always text me, call me, email me, and we can figure this out.